Hello everyone, I'm Deepti Prasad from Azure Database for MySQL product team and welcome to the fourth episode of the Troubleshooting Series. In today's video, we'll be discussing high memory usage on MySQL and how to troubleshoot it. MySQL is one of the most popular database management systems used by developers and businesses worldwide. However, when we start experiencing high memory usage on your MySQL server, it can be quite challenging to figure out what's causing the problem and how to fix it. In this video, we'll go over some of the common reasons for high memory usage on MySQL servers and provide some best practices and troubleshooting tips to help you resolve the issues on Azure Database for MySQL. In today's video, we'll quickly start with an overview of MySQL memory makeup on the InnoDB storage engine, followed by the add-ons available on Azure Database for MySQL to have good memory management. We'll briefly discuss on how the troubleshooting approach should be, followed by some of the commonly seen symptoms, causes, and mitigations that can spike memory on a MySQL server. We'll end it with a quick summary of the best practices. So let's get started with a quick overview of how MySQL uses memory and what exactly is the memory consisting of. Azure DB for MySQL supports the InnoDB storage engine, which is the most extensively used storage engine for MySQL today. In a database, most of the data is stored on disk, but as you know, read and write IO from disk is an expensive operation, and hence MySQL allocates buffers and caches as in-memory structures to improve performance and DB operations. InnoDB buffer pool takes up a majority portion of this memory. It's an area of memory that holds cached data for tables, indexes, and other auxiliary buffers. As you know, MySQL is popularly used in web applications and other OLTP workloads, which are quite read heavy. To improve the efficiency of these high volume of read operations, buffer pool is split up into smaller entities called pages. Basically, buffer pool is a linked list of pages which can hold multiple rows of data. A critical component of MySQL memory management is sizing this buffer pool. It's dictated by a system variable called InnoDB buffer pool size. It's generally recommended that this value be set between 50 to 70% of the system memory. It can also be configured dynamically by the user based on how you want to tune your workloads. But that said, on systems with larger memory, one can further improve consistency by splitting this buffer pool into multiple buffer pool instances. There is another system variable called InnoDB buffer pool instances to configure this dynamically as well. In addition to InnoDB buffer pool, the other components that make up the in-memory structures are something called as temporary tables. These temporary tables are defined by two system variables called temp table size and max heap table size. We'll learn more about temporary tables further down the line. Moving on, the rest of the memory is used for other auxiliary and thread buffers. Each thread that the server uses to manage clients requires some thread specific space. The connection buffer and the result buffer each begin with a size equal to another system variable called net buffer length, but are dynamically also enlarged up to max allowed packet bytes as needed. So Azure Database for MySQL is platform as a service for database management systems where we take the heavy burden of tuning the parameters in such a way that you get a good out of the box performance for most workloads. But that said, you may have to tune them further to your specific workloads. Some of the enhancements that we have done to give you a smooth experience is first up, we maximize the amount of buffer pool space that you get. The buffer pool is almost set to 75% of the available memory on most of the SKUs. Next up, the default parameters are configured to achieve higher cache hit ratio. As a result, memory utilization on your servers may hover above 80 to 90% of the available memory. Our goal is to ensure you have minimal responsibility of tuning. We've also added few features to prevent out of memory as much as possible, like enabling swap and moving MySQL server to the second tier of the OM killer. Even with all the precautions that we've added in place, there can be certain circumstances like the ones listed on your screen that can lead to out of memory crashes. So here's the thing with troubleshooting low memory issues. It's often accompanied by spikes across other resources. Hence, an iterative approach in identifying the underlying cause is going to be the best approach here. Do not start troubleshooting memory if you're viewing host memory metric alone. Unless there is a surrounding symptom like performance hit, slow query, CPU or IO spikes, there's no cause for concern. Eliminate as many basic issues as possible. Ensure that the memory spike or the performance degradation is not because of a sudden workload spike. It's always best to ensure that the recommendations on the CPU troubleshooting, which my colleague Sai covered in the previous video, are taken into consideration whenever memory spike is accompanied by a CPU increase. The goal here is to localize the symptoms and check for possible causes. And once the cause is identified, we can take necessary mitigation steps and add in preventative measures and alerts in place to ensure that it's handled better the next time. From experience, most likely the symptoms and mitigations will be falling into three main buckets. First up, as applications evolve, queries and datasets change and can lead to performance issues causing low memory. Here, the mitigation will most likely be to tune the queries to prevent performance degradation. The next bucket is the set of remedies where MySQL server parameters will need to be tuned to the new workload to achieve optimal performance. This is the biggest bucket, and DBAs play a huge role in maintaining this. The final bucket is the one where the workload and dataset has outgrown the current SKU and will need additional memory, thereby necessitating a SKU upgrade that can ensure large memory availability for your workload. On Azure Database for MySQL, the general purpose tier SKU provides memory of up to 4 GB per vCore, whilst the business critical SKU provides up to 8 GB per vCore, where you can even support heavier in memory operations. So there's ample amount of SKU options for your workload to grow. To progress further with troubleshooting, we need to be aware of the various ways we can monitor metrics and health of the server. The straightforward method to monitor metric on the portal is through the metrics tab. But that said, Azure DB for MySQL provides a wide range of ways to monitor metrics to gauge the performance of your DB instance. You can take a look at the previous episode in the troubleshooting series to comprehensively understand the various mechanisms for monitoring metrics. So let's get started with a commonly occurring symptom that can eat up a lot of memory. MySQL uses what are called as temporary tables to store a temporary result set. These tables get created local to a session. If many sessions are performing compilations of large data sets that are fed through temporary tables, they can quickly consume a lot of memory. Before we dive deep into troubleshooting issues caused by increased temporary tables, let us take a quick look at the two parameters governing the space taken up by temp tables. This is the portal view of the MySQL Flexible Server. If you go to the Server Parameters tab, here you'll find the two parameters, temp table size, and as you can see, this is an editable data. This information is in bytes and indicates the maximum size of internal in-memory temporary tables. Next up is max heap table size. This specifies the maximum size to which user-created memory tables can grow. But do note that MySQL considers the lower value among the two for the maximum size of internal memory tables. In InnoDB, if an in-memory temporary table becomes too large, MySQL automatically converts the table from an in-memory to an on-disk format. So this increase in memory can be easily identified through an I/O spike. And the second symptom that can indicate increased memory stress through temporary tables is from a system variable called created temp tables. It indicates the number of temporary tables created since the last time the server restarted. To troubleshoot low memory issues related to temporary tables, consider the following approach. The first thing to do is to start monitoring the other resources. The first place to start this will be with the CPU. If there is a spike in the CPU, the analysis would gravitate towards troubleshooting symptoms of high CPU loads that I covered in the previous episode. If CPU is more or less stable, the next step would be to move on to I/O and other metrics in finding the possible root cause. Let us take a look at this server's metrics. Let's start with the memory utilization. The memory has been fairly stable, so let's take a look at the CPU. As you can see, there are smaller spikes happening on the CPU front, but nothing of bigger concern. So as you can see, there have been quite concerning I/O spikes going up and beyond what the SKU can necessarily handle. The next big thing for us to do will be to identify what might be causing this I/O spike. Let's see what the query behavior has been. Has there been a sudden increase in workload at this point of time? Let's take a look. So the spikes in I/O do match with the points where there has been a spike in the number of queries that are running. So we'll need to now dig into what within the query is necessarily causing I/O. How can we have more of these queries reading in information from the buffer pool as against going onto the disk? That might be necessarily causing the I/O. So let's take a look at that. Let's start with understanding how many temporary tables are being created. So there are a certain number of temporary tables that are being created, certainly in hundreds. So the next thing to do would be to run this query in periodic intervals to understand what's the trend looking like. Let me rerun this. So this is indicative that the rate of increase of temporary tables is at a much faster pace. So this may be one of the reasons for the I/O spike. Let's also take a look at how many of these temporary tables are getting created on disk. So as you can see, there have been 36 or so that are necessarily being created on disk. This may be indicating a spillage from in-memory to on disk. Before increasing the temp table size value, the next best thing to do here would be to verify that the database is indexed properly, especially for columns involved in joins and group by operations. Using the appropriate indexes on underlying tables limits the number of temporary tables that are created. Increasing the value of this parameter and max heap table size parameter without verifying your indexes can allow inefficient queries to run without indexes and create more temp tables than are necessary. As you recall from the earlier slide, the first thing is the application bucket that we should always be reviewing. After tuning your queries, if you still continue to see an I/O spike, you may want to review the disk temp tables. The value that you set for max heap table size and temp table size parameters may be too low, and this might be leading to this spillage onto storage, adding latency to your queries. This might necessarily be an iterative operation. It might take a couple of trial and error before you find the optimal parameter values for these variables. Once temporary table space is tuned, let's progress into table cache. To improve concurrency in a multi-threaded system like MySQL, there is a need to cache table file descriptors so that tables can be opened independently across multiple sessions. And table cache is where the file descriptors are stored. This uses additional memory but normally increases performance. The table open cache and max connection system variables affect the maximum number of files that the server keeps open. Table open cache is related to max connections. For example, in a server where there are 100 concurrent threads running, the guidance is to specify a table cache of at least 100 into n, where n is the maximum number of tables per join in any of the queries which you execute. You must also reserve some extra file descriptors for temporary tables and files. As your workload would have grown over time, there may be a need to tune table open cache value to prevent any performance impact or high memory consumption. Increase the value of this parameter in increments to accommodate your workload. Setting table open cache too low may cause MySQL to spend more time in opening and closing tables needed for query processing. And on the other hand, setting this value too high may cause usage of more memory, leading to refused connections or failing to process queries. Now let's see if the server needs any tuning on table open cache. First up, let's see what the max connection setting is like. So the maximum possible connections on this particular server is 85. And let's take a look at what the table open cache setting is. So it is currently set at 300. And what this means is that during a max load scenario, so let's take this ideal situation where all of these 85 connections are connected to the server and are querying tables. The maximum number of tables that each of them will be able to query is going to be 300 by 85. So around 3 tables or so can be the max. And beyond that, they will see performance degradation or failure to get new connections and all of the other problems. And let's take a look at what the behavior has been. How many tables have been opened so far? There have been quite a number of tables that have been opened in the past, and this value will continue to increase over time. So open tables is a good status to continue tracking. And just also to do the math, so it will be good to understand how many tables are currently there. So we currently have around 133 tables. And what are the number of current active connections? Not too bad. No, 13 or so connections. So as against maximum connections of 85, currently we're having a medium volume. So far it looks like the current value will not need further tuning. When troubleshooting issues related to low memory, you can also review if tuning of a few more buffers and a cache will help with the situation. First up, let's talk about net buffer, which is identified by the server variable net buffer length. The net buffer is the size for connection and thread buffers for each client thread. Generally, net buffer length has a default value of 16 MB and can grow up to max allowed packet. If a query statement is large, for example, all the inserts have a very large value, then increasing the value of net buffer length parameter will help to improve performance. Next, let's take a look at the join buffer. The join buffer is allocated to cache table rows when a join can't use an index. So if your database has many joins performed without indexes, consider adding indexes for faster joins. And if you can't add indexes, then consider increasing the value of the join buffer size parameter, which specifies the amount of memory allocated per connection. So before we get to tuning parameters, we will need to review the query and check for any application or query improvement before increasing this buffer. The next buffer, that's the sort buffer, also falls in a similar bucket. But here, the sort buffer is used for performing sorts for some order by or group by queries. If you see many sort merge passes per second in the show global status output, consider increasing the sort buffer size value to speed up order by or group by operations that can't be improved by using query optimization or better indexing. Avoid arbitrarily increasing the sort buffer size value until and unless it's needed. Memory for this buffer is assigned per connection. In the MySQL documentation, the server system variable article calls out that on Linux there are two thresholds, 256 KB and 2 MB, and that using larger values can significantly slow down memory allocation. As a result, avoid increasing the sort buffer size value beyond 2 MB, and by default, the sort buffer size value is generally set to around 0.5 MB or so. Moving on to query cache. First up, query cache is only applicable for servers that are on 5.7 as it has been deprecated on 8 and beyond. So query cache is an area of memory that is used for caching query result sets. The query cache size parameter determines the amount of memory that's allocated for caching query results. By default, the query cache is disabled. So if the query cache is currently enabled in your solution, before disabling it, verify that there aren't any queries relying on it. We now come to one of the most critical metrics that's used in MySQL, and that is the buffer cache hit ratio. This value is needed to understand the effectiveness of the instance in supporting the workload. It is indicative of whether the buffer pool can accommodate the workload requests or not. And as a general rule of thumb, it is a good practice to always have a buffer pool cache hit ratio more than 99%. To compute this ratio for read requests, you can either run the show global status to retrieve counters of InnoDB buffer pool read requests and InnoDB buffer pool reads and then compute the value using the formula shown, or you can also access it on the metrics tab on the portal. Azure DB for MySQL provides multiple such enhanced metrics to make your troubleshooting life easier. So let's take a look at the metrics. First up, we have the InnoDB buffer pool reads. Next, let me also add the InnoDB buffer pool read requests. These two values are enough to compute the buffer pool cache hit ratio. There have been a few spikes. Let's calculate the cache hit ratio at one of the points. So here we see two values of 136K and 62K. So as per the formula, the cache hit ratio has been less than 99%. It's hovering around 68.6%. This is generally a single spike, but if you consistently see that the cache hit ratio has been less than 99%, that's possibly when you will need to take action. Now we'll need to dig further into what might be the possible cause here. In addition to the read-heavy workloads that can impact the cache hit ratio, in MySQL, for any DML statements, writes to the InnoDB buffer pool happen in the background as well. However, if at certain points of time no clean pages were available, it will also lead to a wait time for pages to be flushed first. The InnoDB buffer pool wait free counter counts how many times this has happened. So a value greater than 0 is a strong indicator that the InnoDB buffer pool is too small and increase in buffer pool size or instance size is required to accommodate the writes coming into the database. Let's check if DML statements have been the cause for lesser cache hit ratio. So the value here is 0. That means that there has not been a need to wait for the dirty pages to be flushed. And the spike that we necessarily saw was mostly because of the huge number of read queries and select statements that were happening at that point of time. So this might not necessarily entail tuning of the workload, but if this is seen consistently, then there will be a need to tune the buffer pool size so that the cache hit ratio always is optimal. To summarize, the identification of symptoms is through the cache hit ratio computation that we saw, and to also identify if DML statements have been impacting. So one of the resolution steps will be to increase the buffer pool size so that majority of the read statements happen through the buffer pool. But it might also indicate that your workload is hitting the skew limit and you may need a lot more physical memory to handle the incoming workload. So one of the mitigations here can be to upgrade the skew. So now that we've covered the common issues, symptoms, causes, and mitigations on handling memory issues, let us discuss the best practices that you should be following to ensure that the DB is performant. First up, you need to have a continuous process of understanding and monitoring the critical metrics. Next, you should be setting alerts on each of these metrics through Resource Health Center or other avenues that Azure provides. The next process is to periodically review and tune both your application queries as well as parameter settings as your data set grows. There's another set of timely review, but now on user accounts to ensure that the connection limits are in check and don't cause high memory issues. And finally, you need to ensure that the skew is optimal so that there's no performance degradation on the database engine. So, in summary, we need to realize that this is a continuous process, but the heavy lifting is done by the PaaS service, that is Azure Database for MySQL, which provides enhancements and enough channels for you to be better informed about the health of your DB instance. Once you tune the parameters to your workload, all it needs is a periodic review to ensure there is minimal impact of a growing dataset and expanding application. And finally, you are empowered to use as many mechanisms on Azure DB for MySQL, like workbooks, Resource Health Center, or even Log Analytics Engine to collect, track, alert you before the performance degrades or causes any production down scenarios. So that's all I had for you today in this episode. But feel free to go to aka.ms/mysql-resources for anything and everything to do with Azure Database for MySQL. Or if you have any questions, do write to us at the email provided on the screen. We are available on almost all social channels. So do follow us on each of these channels to keep up to date and so that you don't miss any events. Thanks for listening in. I hope this was useful. We look forward to seeing you on our next episode.